So significant digits and estimation. We're going to talk about real world situations that often involve estimations. Significant digits play an important role in making reasonable estimates. So the city is planning a car show, and a section of road is 820 feet long and will be closed to provide space to display the cars in a row. In past shows, the longest car has been 18.36 feet long, and the shortest car has been 15.1. Based on the information, how many cars can be displayed at this year's show? So what we need is we need to know the space available, 820 feet. That's how long the road is. The length of the longest car is 18.36 feet, and the length of the shortest car is 15.1 feet. The word about indicates that we have an estimate. That means we're guessing. We don't know. The cars vary. Some will be long, some will be short, some will be in between. So we're guessing. The available space equals the number of cars times the length of the car. They're going to use the variable L for the number of cars. So the first thing we do is we go, well, what's the longest car? Well, the longest car is 18.36 feet, and that's going to be times the number of cars equals 820. Now, what they did here, they didn't say it, but they divided both sides by 18.36. So what you want to do is take your calculator, and you're going to enter in 820. That's how many feet we have available, divided by 18.36. And it's about 45, right? If I round that up, it's about 45. So we'll say, now you might say, Mr. Adams, why did we round to 45? Well, am I going to have 0.6 cars? No, I'll either have 45 or 46 or 44. So 45 was the closest number. Now, what's the length of the shortest car? What number do I put in here?
15.1.
Yep, 15.1. And so I'm going to say 15.1. See how many times that goes into 820. So I'm going to say 820 divided by 15.1. Hit enter. And I've got, it's about 54 cars. So if I wanted to find the average, and this is all estimate, right? If I wanted to find the average, I could take the number of long cars, which is 45, and the total number of short cars, which would be 54, add them together and divide by 2. Now, you could do this on your calculator by just putting in parentheses 45 plus 54 divided by 2. And you get 49.5 roughly, right?
Yeah.
So 49.5 roughly is about, or would I have a 0.5 car? No, so we'll just round up to 50. You could have about 50 cars displayed. Okay? Now, because the cars will probably have many different lengths, what's a reasonable estimate of a whole number? Well, 50 is reasonable, 49, it depends, right? You could say, I would say 40, you could say 45 to 54. Anywhere in there, right? Are there any questions on that?
No.
All right, let's keep moving. So it says, in this example, why wouldn't it be wise to use the length of the shorter car? Well, the shortest car is probably an anomaly, right? And that's a fancy word that means what? You could overestimate. Remember that said 54 cars? And so you could say may be an overestimate. If one of those cars is longer, then 54 cars won't fit, right? 54 cars, let's put the word cars in there, may be an overestimate. Question number 14. It says, how else might the number of cars be estimated? Would you expect the estimate to be the same? You could average the two lengths of the cars. That's supposed to be a T in there. Let me fix that. In other words, you could say 820, and if you look up here, if we scroll up a little bit, what's the number between 18, 3, 6, and 15? Well, let's just add them up. So you could say 18.36 plus 15.1 divided by 2. Let's plug that in our calculator and see if that helps. 18.36 plus 15.1. That equals 33.6. If I divide that by 2, we get about 16 feet. We could say 820 divided by 17 feet, right? So this is about 17 feet. And so what's 1820 divided by 17 feet? Or not 1820, 820 divided by 17 feet. It's about 48 or 49. Let's just round up to 49 cars. Okay, does that make sense? So we're just estimating. Now, if you guys were planning this and you wanted to make sure you had enough space, would you overestimate or underestimate? Overestimate means you're anticipating more cars. So I would say underestimate, right? Because think about that. You have a certain amount of space on the road, right? If people come to register their car, they're like, I'm going to be a part of the car show, and I say, okay, we can have 54 cars registered, and one of their cars is too long, I can't fit all 54. But if I say 49 cars, and some of the cars are longer and some of them are shorter, I could still fit the 49 cars, more than likely, correct? And who cares if there's a little bit of extra room? So you would probably want to underestimate in that scenario. Anyways, let's do some more estimates here. It says Claire and Juan are decorating a rectangular wall. So let's draw that shape so we can kind of get an idea for it. A rectangular wall. And one type has an area of 9.4. And then there's another one that's wrong thing, bless you. There's another rectangle that's bigger. So one type, it says that there are two types of rectangular pieces of fabric. One has 9.4 square feet. The other has, bless you, 17.2 square feet. How many decorative pieces can Claire and Juan fit in the given area? So let me understand what the question is asking. Same scenario. I have a total amount of square feet, right? And then I have two types of materials that I could fit in the square feet, right? So what they're saying is I have a bigger rectangle. Let me scroll down a little bit. I have a much bigger rectangle like this that's 400, This big rectangle is 433 feet squared. And I could fit so many of these and so many of these. So what do? Well, it's the same problem. We're going to say 433 divided by 9.4, and we're going to say 433 divided by 17.2. So let's just plug these in our calculators, and we'll get some approximations. The first one I'm going to do is if I say 433 divided by 9.4, I get 46, right? If I say 433 divided by 17.2, I get 25. So I'm going to take 25 plus 46, that gives me 71, and then I'm going to divide by 2 to get the average. And so this is about 46, this is about 25, and so I would say, what's 1/2 of that? 35.5. So instead of saying 35.5, let's round it up to 36. Okay? And it says for question 17, given two measurements, if it's possible to be more accurate, is it not the more precise? Let me reread that because I'm trying to read and record and make sure you guys are doing your work. It says given two measurements, is it possible that the more accurate measurement is not the most precise? And then it says, well, what do you guys think? Yeah. And then you're supposed to give a scenario. So it could be one over measures, and these are not real math words. One over measures while another under measures. That's the easiest way to say it. Problem number 18 says, what's the relationship between the range of possible error and the measurements used in the calculation? And the range of possible errors in the calculated measurement. So what they're referring to is if I measure something and I measure too much and I measure too little, that's what we've been doing all this time. There's a possible error. Maybe I over-measured something, maybe I under-measured something. But when I go to take and make a calculation, how does that reflect in the range of possible error in the calculated measurement? So the answer is the range, you guys should be writing this down, the range of possible error in the calculated value is greater. And let me explain what I mean by that. If we scroll back up at the very beginning of this thing, we did an example where we measured a pool, right? And so we measured the pool. No, wait. Where's the one where we did the more and less? It was way at the beginning. Let me scroll. It was before that. The example before that. It was our first example. This one here. Remember, we did this measurement of we were calculating the area of a rectangle of a book cover, and we said that we thought the minimum length was 28.3, and then we plussed or minused a certain amount, and then we found that the maximum length could have been another number, which was 21 point. Actually, I said that backwards. The minimum length was 28.3 minus 0.05, and the maximum or the minimum width was 21 minus 0.5. Right? Remember this?
Yeah.
And then we did the same thing with the maximum width and the maximum length. Well, when we multiply those together, remember the area was, look at the difference in the area. So this was like the minimum area, and this is the maximum area. So we looked at the error in this plus or minus 0.05. This is the error. And then this was the error on this measurement. And when we multiplied, those errors got multiplied too. And see the big difference? It goes from being a half a centimeter to almost 30 centimeters difference, right? So what they're saying is when you have an error in your measurement and you do like the volume or the area, you're multiplying that error. So your error is greater in the calculated values than it would be in the actual measurement errors. So then 19 asks, how do you use significant digits to determine how to report a sum or a product of two measurements? The sum, a sum, should be rounded to the same place value as the last significant digit.
Can I just put sig fig?
Yeah, we could do that, sig fig. So that's the sum. That means when we add it. A product, that means when we multiply the numbers, should have the same number of sig figs as the least precise measurement. Okay? Does that make sense to you guys?